Welcome to the Abstract Synthesis podcast, where we share the stories behind interesting academic papers in the world of program synthesis. Brought to you by AGI Research Lab and DIA. I'm your host, Brian Landers.
Mark Santolucido.
And today we have a very special guest. Professor Moshe Vardi is one of computer science's most decorated theorists, holding tons of awards. Just this year alone, Mark, you've been at some of these conferences, but CAV Award, International Conference of Database Theory Test of Time Award, the IEEE Computer Science Prestigious Computer Pioneer Award. That's just this year. We'd spend the whole episode talking about other honors and awards if we covered that. But that's not it too. 700 technical papers published, more than 64,000 citations if you look on Google Scholar, spanning across logic, databases, AI, program synthesis. This is a really special guest, and we're very excited to welcome you. So welcome to the show, Moshe.
It's a pleasure to be with you.
Oh, I forgot to say, also, Moshe, you are well known for your kind of societal and like larger picture takes, things like predicting 50% unemployment within 30 years. So feel free to mention anything you'd like during this episode. There's nothing is off limits. Fair?
Let's keep, my rule is no politics, sex, and religion. Okay.
That's the party rule, right? Like things not, and traffic. Traffic is the other one, right? Well, Mark, what paper are we going to be focused on today from Moshe?
Yes, so today we're going to be looking at a paper, Symbolic LTLf Synthesis. This is a paper that I'm a huge fan of, actually. I myself work a lot in temporal logic, and the finite version of LTLF has been getting a lot of attention recently, has a lot of really positive benefits compared to the more, let's say, traditional LTL approach where you're looking at a infinite horizon.
So I guess to kick things off, we're talking about symbolic LTLF synthesis, Moshe. What is the genesis of this paper? What sparked you to decide to write this?
This paper has amazingly deep background, okay? And so for this, you have to go first to even foundation of mathematics, okay? And you're looking at, you're trying to study like the nature of, it's called actually part of set theory, the very foundation of mathematics. And imagine we play the following games. We start with a set W of numbers between 0 and 1, real number between 0 and 1, and that's the winning set, okay? And now we play a game. We take a piece of paper and we write on it 0 point. And now we take turns writing digits between 0 and 9. I write 1, you write 1. I write 1, you write 1. And we play this game forever. So at the limit, what you get there is infinitary expansion of a number. So it's a real number between 0 and 1. If that number is in the winning set, I win. And if it's not in the winning set, then you win. Now, the question is, do we have winning strategy? Ideally, what you would like in a normal game that you're familiar with, in finite games in particular, in a finite game, one of the two players has a winning strategy. Why? Because you look at the game tree, there is a finite game tree, and you start from the bottom, you label it who wins, and then you go up, and each one, if I can move to a winning position, then I win. If you can move to winning position, then you win. So we can analyze and we get to the root, we see who wins the game. So in principle, you take the finite game tree and you do bottom-up kind of induction and you decide at the root who wins the game. And one of the two players will win the game, okay? And such games are called determined. We're guaranteed that one of the two players has a winning strategy. But now...
The counter example would be like tic-tac-toe, right? Where, you might end up with a tie. That would be a game that's not determined.
Yeah, that would be a game you may not have a winning strategy. But if it's a finite game, it's a normal finite game, then you do and every configuration at the end has to be winning. Final configuration must be winning for somebody. Then the game is determined. But what about infinite game? We cannot do this backward induction if the game tree is infinite. So we said for finite game, the game is determined. What about infinite game? Why are infinite games of interest? You say, who cares about infinite games? It does not sound like a real life game. Well, the answer is that when the people start looking to foundation of mathematics in the late 19th century, become clear there's one big problem in mathematics in the foundation. It's the infinite. It's a very strange object, the infinite. Does it exist? Is there an infinite? Okay. This is a big philosophical debate. Yeah, we can keep counting. But does it mean there are infinitely many numbers? Some people say, no, you keep counting, but there are no infinite, we cannot comprehend the infinitude. Other people almost use religious argument. God can see the infinity of numbers. So this was a huge controversy in the late 19th century about the nature of the infinite. So set theories study in particular the infinite thing. And so they ask about infinite games. And then there is a result, I think it's from the 50s, I don't remember the exact date, by Tony Martin. And that if the set W of winning sets is a Borel set, it's a particular type of set, then the game is determined. But there are sets for which the game is not determined.
Makes sense.
So on one hand, people start studying, and it's a beautiful theorem to say if the set, because Borel sets are in some sense constructive, we cannot understand how you construct them. So such set that we can construct, the game is going to be determined. So this is development number one. And then another development is we have Alonzo Church, who was a mathematician in Princeton, and he's famous for doing studies in the foundation of computability. You know, when people decided in 1930 to define computability, Church came with two formulations. One is using recursive functions. The other one using the lambda calculus, which is a particular formalism for defining functions. And there were debates whether these are satisfactory definitions because, yeah, okay, but why should this be good definition of computability? Then Turing came up with Turing machines, which was the description how mathematicians compute. It's an abstraction how mathematicians compute. And it turned out the Turing machine's computability is equivalent to recursive function and lambda calculus. And that kind of settled the question practically. We still call it the Church-Turing thesis because it's not a theorem, it's a thesis, okay? And then this was in the 1930s. And so computers there are completely theoretical objects, okay? There are no computers yet when they do that. That's pretty amazing about it. I mean, there are no computers.
It's hard to imagine
when they
these
define,
days, you know,
you got
these things.
Yeah. I have an interest talk on YouTube. You can look it later. It says from Aristotle to the iPhone.
I love that. Okay, we'll definitely link that.
When I try to look at the like 2,500 years of history of how we went from Aristotle to the iPhone. But in the 1950s, Church read about this new technology, electronic circuits. And in particular, he was interested in what we call today sequential circuits. So sequential circuits are really the foundation of what we have today. Every computer is sequential circuit. Sequential simply means it has memory elements. So at each point, you look at my computer, each point you get some signals. You know, the network packets, the voice, the keyboard, whatever, all the input sensors. So it essentially gets a bunch of bits. And what does it do? It gives me back a bunch of beats, which is on my screen or the sound or vibration or what have you. Okay.
Yep.
And it changes its state for the next cycle. So this is essentially what a sequential circuit does. It gets input, it computes output, it computes a new state. And then Alonzo Church asked, how do we specify correct behavior of such circuits? Okay. And he said the output of such a circuit is a trace. What is a trace? It's simply the infinite sequence of input, output, and state signals. Triple. You have it for each moment, and we're assuming a clock circuit. So there is a very clear tick-tock, tick-tock. There is a notion of, there is a clock, so there are cycles. Every cycle, there is a triple, the input assignment, input values, the output values, and the state. He said, okay, so we have an infinite trace. How should we specify this? And he comes up with a logic, which is an extension of first-order logic. First-order logic is the kind of the standard logic we typically use. But he argued that we need something a bit more powerful. And it's called monadic second order. And he asked two questions there. One, if I give you a circuit and a formula that describes correct behavior, how do we prove, can we prove that this circuit really behaves correctly? That is, regardless what the inputs are, the final trace would obey this specification, would meet the specification. So this is the verification problem.
But of an infinite trace, you had said.
Everything is infinite.
Okay.
Why?
Okay.
Because the circuits are supposed to run forever. So, I mean, you look at your laptop. In principle, it's supposed to behave as if it will run forever. Of course, you and I know that at some point the disk will fail, the battery will die, what have you. But in principle, you say, look, I have this computer, it should be able to run forever, okay? If nothing bad happens. So let's just abstract and presume that this will run forever. The second question is, if we have, you say, wait a minute, if we have this formal specification of the circuit is supposed to behave, why can't we design it algorithmically? Start from these properties, this monadic second order or MSO sentences you want it. This is how it's supposed to behave. And now we want to design such a circuit. This is synthesis. So here's the first one that says, can we synthesize programs, if you want? He was focusing on circuits. Can we synthesize programs from a logical specification how they're supposed to behave?
Could you give us a little bit of insight just before we move on? I think we're probably familiar with first order logic. For all people, there exists a parent of that person. How can we think about monadic second order logic?
At the second order, you can also quantify, you can say there exists a set of points on the trace, or for all sets of points on the trace. For example, I can say there exists a set of points such as if a point is a set P of points, such if a point is in the set, then its successor is not in the set. And if the point is not in the set, its successor is in the set. And point 0 is in the set. So now it must be exactly all the even points. Okay, I can say something happened in every even point. And the concept of evenness, I cannot express it in first order logic. Turns out I cannot describe it. I have to have this pacing mechanism. Yes, in, out, in, out, in, out, to get the concept of even. Okay?
It's really cool.
So Church asked these two very important questions that kind of, in some sense, laid the ground for much of the research in formal methods. We are talking about now almost 75 years ago, okay? So we are asking, can we verify circuits? And can we synthesize circuits? So that's really, in some sense, the area. I mean, some ideas are reinvented, so to speak. So the concept of verification came up later with like Hoare and Floyd, and other people came up with program verification. But Church was thinking about circuits, not about programs. He wasn't familiar with programming yet, but he looked at circuits. And the nice thing about circuits, they have a very clear logical semantic, because circuit is just Boolean logic. So he understood logic. Okay, you don't need to know what is the semantics of programming languages, which is a complicated topic. Here,
Yes.
it's a Boolean circuit with state, and he says, can we verify them? Can we synthesize them? So he posed this question. I think it's the paper is, I think, not 19, I believe 1958, I think, if I remember correctly, 1958.
Okay. Huh.
So people say, okay, now, once you have defined them, these are questions in logic. We don't need to know anything about circuits or anything like that, okay? This is now question for pure logicians, okay? So logicians start thinking about it. And the first question was the verification question. That's an easier question. And that was solved using automata theory. Okay. So what is automata theory? So for this, first of all, you have to go back to Turing's 1936 paper, where he asked, what is computable? And his answer was, well, in fact, until that point, until the 1940s, in fact, when you use the word computer, you refer to a person who computes. It was a job description.
Ah,
A person that computed was a computer. Okay?
wild.
If I say surveyor, it's a person who does survey, right?
Right.
So a computer was a person. In fact, not only a person, most likely, a woman. Because this job were one that require patience and precision, and this were perceived that women are better at these kind of jobs.
This is the NASA Hidden Figures.
This is part of the NASA, exactly. This is part of the hidden figure that all the early people in programming were women. And there is interesting story. What happened? How did they disappear? How did the men took over? How did the men took over?
And this is Moshe. This is a big deal, and we're growing our team around this program synthesis work, and it is just like, I've never seen a field where it's so hard to get more diversity in terms of talent.
Very hard. But I've written something about how we lost the women in computing, and the answer is actually this is historically studied. They've been pushed out. After World War II, the men came back from the war. They need a job. These are good jobs. Men are supposed to provide, and women have been basically pushed out. I put it also kind of a bit tongue in cheek. If you look at the early programming, when like the ENIAC, the very first machine, it was not coding. To write a program, you have to set switches and connect cables. And if you did one switch wrong, it will not work. So it required tremendous patience and precision. And only women were perceived, I don't know about whether this is verified, but the perception was that only women have the precision and the patience to do that. Only later, programming became coding, and then it became easy. When it became easy job, then men took over. When it was hard, it was done by women. When it became easy...
Vardi theory of gender and coding.
Yeah. But Alan Turing started thinking about computability in the 1930s. And again, it's completely motivated by foundational questions. Okay. Hilbert believed, he said, look, think of all the math that you do in high school, algebra. You're basically given recipes to do computation. I give you a set of linear equations you're taught in high school. This is how you do that. Nobody used the word when you learn high school algebra. Nobody said, we're giving you an algorithm to solve linear equations. But that's what they did. They gave you a recipe. This is how you solve it. Okay? So why should we not expect that all mathematical problems can be solved in such a way, using mechanical calculation? And so this was the belief of Hilbert in the first third of the 20th century. But what does it mean that mathematics is mechanizable? We had to define computability. And the project took places in a few places. I mean, it wasn't in one place. We mentioned Church in Princeton. There was Emil Post in New York, Kolmogorov in the Soviet Union, and Turing in Cambridge. And Turing said, well, let's see how does a human compute. Human have a sheet of paper, write symbols on them, read the symbols, has to remember, for example, you remember the carry, but you don't have to remember too much when you do computing, because we know that working memory for a human being is 6 to 7 items. This is what psychologists tell us. Okay? If I give you, that's why, for example, if you look at two-factor authentication, usually they're giving you six digits. If they gave you 8 digits, that will already make it difficult to remember without copying one after the other, okay? So it stretches our working memory. So Turing says we have finite working memory. So he said, well, we write on a sheet of paper, but we can take the sheet of paper and make it into a tape by cutting it into strips and taping them. And so we come up with a definition of Turing machines. Okay. So we have a definition of computability. At the same time, he's arguing the brain is not a Turing machine. This is a question that has come up early on. What is the brain? So the brain is not a Turing machine. This is in 1950 when he asked, can machine be intelligence? And he argued that the brain has finite capacity. Even though the brain is an analog device, the neurons have a finite resolution. Okay? Maybe they can distinguish, I don't know, I'm making up a number. Let's suppose they can distinguish between 1/100th of a volt difference, but not 1/1,000,000th of a volt difference. Okay? So he said the brain has finite capacity. It's a finite biological construct. Okay, there are so many neurons, and the neurons have finite resolution. Therefore, the brain is a finite state device. Now, Turing machine, in contrast, have this unbounded tape. Okay, so Turing machine does not have bounded memory. The tape the tape is in principle infinite, but the brain is finite state. And so in the 1950, people says, well, let's study the computational power of finite state devices. And that's why we talk about finite state automata. They're really finite state machines, finite state automata. What happens if you only have finite state? So automata theory start in the 1950s, looking at and they try to define what is the computational power. The simplest way to do it, you have such a finite machine, and you give it an input tape with symbols. And it should read it and say yes or no. So, for example, you're giving a word or a sentence. Is this a proper sentence in English? Okay, this is a very important question in natural language processing. What is a proper sentence in English? Turns out, actually, it's very hard to define formally. I'm a second. English for me is a second language. Sometimes when I really want to know if something is sound correctly, I have to go to a student who is a native speaker. I say, does it pass the ear test?
The ear test.
The ear
Interesting.
test. Ear test. Does it sound right to you? Okay. This is the best test ultimately to what is a sentence. But can we have a machine will have finitely many states? We'll read a sentence, we'll read it symbol by symbol, and at the end it will say yes or no. So this is kind of a very reductive view of computation and just recognition. It's a yes or no. Okay? And so people starting to study the recognition power of finite state machines. And again, the model was, at that point, people were still feeding computers with tapes. So that's why they said, let's feed this machine with a tape with symbols. Before we had punch cards, we had punch tapes. That was the original input device. Punch tapes, you fed the machine a tape. Punch cards were a great invention because they were much more robust than tape. Tape you would tear easily, so punch cards were progress. I did my first programming still with punch cards. Sounds
so cool.
Sounds like the Middle Ages, but we still did that. And so that's why the definition was, we take this tape, paper tape, we give it to the machine, and it has to say yes or no. So that theory is in the 1950s. For example, there was a famous paper by 1959 by Rabin and Scott on foundation of automata theory. And in fact, that's the paper led to their receiving the Turing Award. It was a very important paper. That paper introduced non-determinism that led up to NP completeness theory. So that is in 1959. Now we are going back to Church's problem of verification, and Churches assume that the circuits run forever. So a Swiss logician, Richard Buchy, but it's hard to pronounce the name, so I'm just going to be lazy and say Buchy. It's CH, and it's UE and the CH.
Oh boy.
And you have
There's no hope.
You have to pronounce it like not just in German, in Swiss German to get the
Swiss German.
Swiss Deutsch. So it's
the ear test will fail here. Just don't bother.
So I will just say Buchy because it's just easier for me to say Buchy.
Okay.
But Buki said, wait a minute, why don't we take this automata and let them run over infinite worlds? Because I'm interested in infinite behaviors of these circuits, a behavior that runs forever. So he introduced automata that become known as, after him, as Bushi automata. And these are automata that look very much like automata that Rabin and Scott study, finite set machines, but you give them infinite input. But there's no, when a finite tape, there is a moment of decision. At the end of the tape, you have to say yes, no. So what happens if I give you infinite tape? So the answer is, along the way, you have to say yes or no. And if you said yes infinitely often, then it's a good. You accepted that infinite word. You said yes infinitely often. Okay? So we are not talking about creature that lives forever. Still, what happens when you go to after you read infinite tape, and people say, how can you finish reading infinite tape? I tell them very simple. You read the first symbol in 1 second. You read the second symbol in half a second. You read the third symbol in 1/4 of a second. And within 2 seconds, you'll finish an infinite tape, right? Because 1 plus half plus quarter plus 1/8 sums up to 2. The limit is 2.
There you go.
So Bushi defined this notion of what we call acceptance in the limit. Okay? So we started with very almost physical intuition, but now we're creating abstractions, but they are very solid mathematical abstractions. And then Bushi used this theory of Bushi automata to prove that the verification problem is decidable. He came up with an algorithm to solve the verification problem. So he answered Church's first problem. Yes, we can prove there is an algorithm. It's computable whether a circuit satisfied the specification in monadic second-order logic, where you can quantify over points and over sets of points. The other question was, okay, what about synthesizing it? And now people are saying, wait a minute, how should we even look at it? And they go back, remember the notion of a game where two players play a game, okay? So they says, well, let's imagine now we're playing the following game. We have the MSO formula that describes the relationship between inputs and outputs. So let's play a game. At each moment in time, you set the inputs and I set the outputs. You set the inputs, I set the outputs. And we go on forever. Now, I win the game if I look at this infinite race. It has to satisfy the formula. It had to meet the specification of that was written down by an MSO formula.
Be the correct. Yeah, the winning strategy. Yeah.
So first, you have to win. So the question is, do I have a winning strategy? Do I have a winning strategy? That to say, is there a way to systematically go from inputs to outputs in a way that if you do it forever, now it's a game that goes forever again, but I'm guaranteed that the specification will be met. So this is very similar to the game we mentioned before, but now it's in terms of a formula. So these are known as MSO games. And people prove important result. One, again, this is decidable. There is an algorithm to decide if the circuit has a winning strategy. But the other very important result was you start from this logical specification. I don't want just an input as a winning strategy. I want a strategy can describe as a circuits. So it has finite memory. So I want to have a finite memory strategy. I want to have a finite memory strategy because if I have a finite memory strategy, then I can build the circuits. If I don't have finite memory, then I cannot build the circuits. I'll have to have like an infinite, I have to have maybe a circuit, but with this drive that will get, imagine if you live your life and every decision you make have to take into account every moment in your life so far. Okay? You have
Terrible.
to- everything, you have friends, you guys work together, and when Mark asks a question, and when you, Brian, are going to answer him, you have to take into account everything that Mark has said since the beginning of time.
It sounds you'd never finish lunch. You just like sit there forever.
You never finish any question. Good morning. What is the right response? I have to take into account everything he has said since I've known him. Okay. So we want to have finite memory of what do I need to remember about him. Okay. I need to remember that he wants enthusiastic response. Okay. Good morning to you too. Okay. That should work. Okay. So the result that is already proven in the 1960s is that MSO games, one, they are determined. So we can decide if there is a winning strategy. And if there is a winning strategy, there is a finite memory strategy. Okay? This is amazing result because now we say you want to build circuits, just write down your specification, and we can now have a compiler, so to speak. They will take this behavioral specification and convert it into a circuit. There is only one little problem.
Always a problem.
And this is the computational complexity. Okay? The computational complexity is what we call non-elementary. What does it mean? It is not an exponential. It is a tower of exponential. It is 2 to the 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 n, where the height of the tower is n. If the input is of length n, so if the input is of length 2, it's 2 to the 2. Okay. If the input is of length 3, 2 to the 2 to the 2, which is 2 to the 4, so it's 16. Okay. The next 2 will be 2 to the 16, which is 64,000, I think, if I've done my calculation right. And the next one will be 2 to the 64,000, which is more than the number of elementary particles in the known universe. Okay. So some people call it cosmological, not astronomical, but cosmological numbers. Okay, because the numbers are just so astounding. So that result, in some sense, was a nice mathematical result, but nobody thought this can be of any use. Okay. So this is chapter 1, very interesting story, but it ends up, people then improved. Michael Rabin came up with algorithmic simplification, but it kind of stabilized by the early 70s, and it's a nice theory, but nobody expected to have any application. Okay. The second story, we have to go back to Christchurch, New Zealand, in the 1950s. And we find a philosopher, Arthur Norman Pryor, who wonders about the nature of time. He's a philosopher. He wonders about the nature of time. And he says, well, we have to be able to, time is such a slippery concept, we don't even fully understand it, but let's try to see how people talk about time and develop a logic for time. And so he came up with something called tense logic. Today, somehow tense became temporal logic, but he called it the beginning tense logic. Okay. And so there is a lovely, there was an interview after he died with his wife, and she remembers where he came to her bed. So apparently they slept in separate beds, and he woke her up to tell her that he invented a new logic. And I just find it such an endearing little story. Imagine, it's not just you're so excited. You don't wait till tomorrow morning.
Honey, wake up.
You wake up your wife to tell her, I have invented a new logic. Okay, very, very endearing. Okay. I'm not sure how tolerant my wife would be if I woke her up.
She's like, yeah, whatever. Go back to bed.
Tell me in the morning. Okay. You woke me up for that, for logic. So it's just an endearing story. And he goes on and he ends up publishing a book on this. He goes to Oxford, he gives lectures. Even though he's done other things, this is his major claim to fame. He invents tense logic or temporal logic. And even he starts realizing, this might be relevant to computing. Okay, we're heading into the 60s, there are circuits. he heard, when we do circuits, we do sometimes there is concept of time delay analysis, because in logic, when you do Boolean operation, it takes zero time. But when you build the real circuits to do an end, you have to charge two capacitors, okay? You have to charge capacitor. It takes time. Everything takes time. We're not dealing with mathematics, we're dealing with physics, and everything takes time. So when you build a circuit and you have a clock circuit, you want to make sure that every logical computation can happen within one clock cycle. So people do time delay analysis. So people, even the philosophers, this may be relevant to computing. But then in 1976, a Israeli computer scientist, Amir Pnueli, said, I'm interested in not just, people talk about verification starting even in the already Turing, in fact, wrote the first paper on verification in 1949. But they were typically looking at program in the traditional sense. The program has inputs, it computes, it ends up with an answer. How much is 6 times 7? The answer is 42. Okay, but by the 1970s, we realized that's not all of computing. CPUs are supposed to run in principle forever. Operating system run forever. Communication protocols run forever. We cannot talk about input and output. It's a sequence: input, output now, next moment. So now we're looking at arbitrarily long traces. And let's just abstract and say infinite traces. And Pnueli discovered this work by Prior, and he said, let's use it to reason about what we call ongoing program that run forever. So he defines LTL, Linear Temporal Logic, okay? And now some people have a new interpretation of LTL. They call it little tricky logic. And the reason is they have done user studies. And it turned out that students, it's not so easy to go from the formalism to what does it mean in natural language and vice versa, okay? That's why I call it little tricky logic.
That's fun.
So Pnueli introduced this, other people have introduced it, philosophers studied it. Pnueli said, let's take it and move it to computer science. So that paper from 1976 is the beginning of temporal logic in computer science, until then it was all in the realm of philosophy. Okay, suddenly now it's part of computer science. And that has kind of continued to evolve. In particular, remember that we mentioned before that there is a connection between MSO and Bushy automata. Well, it turns out that LTL is really equivalent to first order logic. So it's a very special case. It's weaker than MSO. It's actually equivalent to first order logic. Okay. However, so the same way that we can go from MSO to Bushy automata, we can go from LTL to automata. However, while from MSO to automata, we say it's non-elementary, 2 to the 2 to the 2 to 2, an unbounded tower of exponential. Turns out that for LTL, already in the early 80s, Pierre Wolper and I showed it's a single exponential. Now, typically we think exponential is bad. We talk about exponential blow-up. But hey, we started with non-elementary, which was an unbounded tower of exponential. A single exponential sounds like really, really good news. Also, people start doing experimental work. And it turned out that the exponential blow-up is a worst case. Yes, you can write formulas for which going from the formula to the automaton will be exponential blow-up. But for many formulas you encounter in practice, it does not happen. So this connection between logic and automata that was really completely theoretical, in the 80s, suddenly become actually practical. And by the end, this started in the 80s and developed further in the 90s. And by the end of the 90s, there are industrial tools that build on this technology. They take computer circuits, they take properties written in LTL, and using the automated logic machinery, they tell you yes or no, does the circuit meet the specification or not. And if it doesn't, you give your counterexample. This became known as model checking. And this is today industrial reality. In fact, around 2000, in the late 90s and early 2000s, I was doing consulting with Intel. And the project I was involved with to say, okay, LTL is a nice academic language. Now let's build an industrial specification language. And so there's a process. In fact, several companies at that time developed industrial specification language. And then there was a standardization process that led to industrial standards. And today there are two industrial IEEE standards. One is called PSL, Property Specification Language. The other one is called SVA, System Verilog Assertion. System Verilog is the dominant language for circuit design. This is a language for assertions for system Verilog models. And today, these are the industrial tools that support it. And in fact, one of the awards that you mentioned at the beginning, the CAV award, was for that tech transfer, for taking very theoretical work and taking all the way to industrial standards.
It's very impressive. Yeah.
Okay. So this is today an industrial reality. So sometimes now, already in the very late 80s, Pnueli himself said, wait a minute. If we have now this automata theoretic approach for model checking, why can we not go back now to Church, the second problem, what we call Church's problem, and do synthesis, starting from LTL? And he writes papers, and he showed that this can be done. It's not going to be non-elementary. It's going to be two exponentials. And eventually, it is shown that you cannot do better than two exponential. What is two exponential? 2 to the 2 to the n. Two exponentials. Okay? Two exponentials is pretty bad. Okay? If I take 2 to the 2 to the 10, okay? 2 to the 10 is about 1,000. So 2 to the 10 is 2 to the 1,000. That's just a cosmological number already. Okay? So double exponential is considered to be very, very bad. But at that point, people say, wait a minute. This is the worst case. What will happen in practice? Okay? Model checking started with also being hard, but in practice, we showed it's not so hard. Let's try to do synthesis. So sometimes and then people start again hacking at the problem. Trying to look at various algorithmic building blocks. Let's try to improve this. Let's try to improve that. And then people start building tools. And today, for example, there's an annual temporal synthesis competition. Okay? Turn out that we've made progress, we're clearly making progress, but we're still, I would say, far from having tools that are scalable enough for industry to say, okay, we're going to use it now. Like model check industry says, we'll take, this is good enough for us. We can take over and start building industrial tools. That has not yet happened. It was for temporal synthesis. However, in 2013, a colleague of mine who's worked more in AI rather than formal method, he's coming from the AI side. And he said, look, you guys are obsessed with this infinite traces business because you want to abstract, you want the most generality. I mean, coming from AI, when we want to synthesize a plan, we want something that will finish in our lifetime, okay? We're not saying, do something will run forever, okay? Build a robot that will, go through the building, clean up all the door, all the rooms, and declare victory when it's done with the building, okay?
Exactly.
I'm not trying to design a robot that will clean the building forever, okay? I'm happy to reset it once a day. Let it start from scratch. So he said, can we try to look at LTL over finite traces instead of infinite traces? And I said, yeah, I mean, I was kind of more coming up from the theoretician point of view. where we like the mathematics to be also non-trivial, okay? Because, the ultimate insult to a paper to say, oh, this is a trivial result, okay? Somebody comes with a result and you say, oh, this is trivial.
I thought it was, that's semantics. We're just arguing about semantics. No, I'm just kidding.
Semantic actually for logicians, semantic is important.
Okay, okay.
But
I'm learning.
But trivial, actually, you know where the word trivial comes from? It has a very interesting history. Think about the root. Tri, what is tri? Tre.
Three?
Three, exactly. What is via?
Life?
No, not
No.
life. Via Dolorosa, what is via?
Way?
Way,
Road,
way,
okay.
road, way. So, three via means the three ways. So in classical liberal art, medieval liberal art education was divided into lower division and upper division. The lower division was grammar. You have to speak correctly. Logic, you have to speak the truth. And rhetoric, you have to speak convincingly.
Okay.
That was the trivia. The upper division was the quadrivia, and that was arithmetics, geometry, astronomy, and music.
Hey, music. I love it. We made it.
That was the quadrivia, the four ways. So the three ways were considered to be the stuff that everyone is supposed to know, the lower division stuff. So that's why today we say something trivial. Okay? And today, when you say something trivial, it is dismissive. But it started something very important, something so foundational. Everyone must know it.
Necessary, yeah.
So we have, I was interested in non-trivial result. And when you go to infinite words, the theory is much richer. So when he first told me, let's look at LTL over finite-trace, I said, it's going to be, everything is simple. And he said, simplicity is a feature, it's not a bug. It's good for things to be simple. We don't need, if we want to use something, then simplicity is good. So we wrote a paper in 2013 defining what we call to the LTLf, which is LTL over finite traces. And that paper kind of, in some sense, now we are about 12 years later. And that paper has now, it's closing on about 1,000 citations. And 1,000 citations is kind of a mark for a seminal paper, okay? I look at how many such papers do I have, and this is one of them, okay? I have maybe 10 such papers, this is one of the 10, okay? Seminal papers, 1,000 citations. So we continue to write a few more papers, again, on the theoretical aspect of this logic. But in 2017, I had a Chinese student visiting me and wanted to do some research with me. And very often when I start with a new student, I don't know their capabilities. What are they capable of? So I'm not going to kind of throw a big problem at them because I don't know what are they capable of. So I usually start with something that in principle I know how to do. So I can guide them and I can just tell them, do this, and you'll get the solution. And I told her, why don't we try to take this logic LTLf and we will try to do synthesis. And here is how we're going to go about it. We're going to leverage some existing tools. So here is how you're going to go about it. And that's how we wrote this 2017 paper. Okay? Here's how you go about it. And again, we had a good strategy to implement. It didn't require an enormous amount of coding because we are building on existing tools, other tools we brought to the picture. But the important thing is we discovered that because the simplicity of going back to finite rather than infinite, which is, I said, oh, it is simple. And when I say it is simple, I was a bit derogatory, kind of almost to say it is trivial. But simplicity means it is more scalable.
Yeah, tractable, right?
It's more tractable, yes. Tractable. I use scaling now. Scaling now is a big word in the AI world. That everybody wants to do scaling.
Yes.
So it means we can deal with bigger problems. Scalable to me means we can deal with bigger problems. And so that kind of started, other people say, oh, and it doesn't seem to be, the entry barrier is not as high because the theory is simpler. So there are other tools. And today the temporal synthesis competition has an LTLF track.
There you go.
And in fact, we will have in October another paper, which I'll send you later if you want to point to it. We talk about engineering an LTLF synthesis tool. Again, main focus what we call algorithmic engineering. We understand the theory, but we just need to do better algorithmic engineering to get better performance. And the hope is that we will get to performance which will be good enough for industry to say, now we should look at it and we should start to build industrial tools. So if you understand, in academia, we kind of have a challenge. There is a word that I heard recently, and you've never heard of it, I'm sure. You've heard of hardware and software. Have you heard of gradware?
Where? No, it's a new one.
So what is gradware?
Have you, Mark? Have you heard of this one?
Hey, I've got some ideas.
So gradware is software that's built by graduate students. And why it is a category? Because graduate students have to have one nasty habit. They graduate. And when they graduate...
Abandoned.
And when they graduate, they usually move on. So they build this tool, and then they move on. Now...
Like a graveyard of GitHub repos.
So now you have it on GitHub, but this is the code. And you can't just give it to another student to say, okay, why don't you just improve it? Because usually we want the PhD dissertation to have some novelty. Here is I was the first to solve it. Mm-hmm. So it's a bit more difficult to say, okay, why don't you just improve it? And okay, what's the research? What's the dissertation? How will I get a PhD for it? So GitHub is full of gradware. And what happened when the code just lies there, the bits start to rot. For example, every piece of software has some dependencies. You depend on other packages, but they are not your packages. So actually, part of the problem, we have not developed good practices for just archiving stuff. The answer should be, if you put something on GitHub, you should archive all the dependencies, everything.
Oh, yeah, that's good. Yeah.
Otherwise, you depend on a software that's also gradware, and somebody will change it, and suddenly your code is not running anymore.
It's like the opposite of the Git ignore. It's like the Git pay attention or whatever, yeah.
And not to mention that you may depend on some Linux features, and suddenly Linux changes, and the code that used to run doesn't run anymore. So it's very hard to get code into. In fact, there is something called the Software Heritage Project. And these people said software today is a major cultural heritage of our generation. The same way that we are preserving culture, we think we should preserve our cultural heritage. Important piece of software should be preserved. And when for example, when you preserve manuscript, you should keep it in dry air. Humidity is not good for manuscript. So they're developing the practices to preserve software, how to archive software.
Fascinating.
So in 50 years, people will be able to run this software. It's not so simple. Take 50 years old software, try to run it, okay?
Cool project.
So one of the things that the success that happens with model checking, some industry says, okay, this is mature enough, we're going to start developing industrial tools. And that will be the success that we've transferred all the way from the people who wonder about the nature of the infinite and look at infinite games and, do they have a winning strategy and Borel sets and all kind of such very esoteric things. If at the end we're going to get that the goal is ultimately to have goals for designing circuits. This is really what Church's problem. Can we design circuits using these tools? Can we kind of going back to, we want agents, everybody is not talking about agentic AI. Can we have agents where we tell them these are the requirements in some formal language, and I can be guaranteed that's what they're going to do. Even though they're going to deal with all kind of contingency along the way. If everything happens according to plan, it's easy, okay? Life is complicated because stuff happens, right? Stuff happens. The robots go to there, but that door is closed, okay? What do you do then, Okay, so can we get to the level of we have, autonomous agents? Think of people talk about like deep space missions. Okay, where even just mission to Mars, I believe a signal to Mars is 20 seconds. I think 20 seconds is a long time. For if you're trying to push a button on Mars, you push a button here, 20 seconds before it pushes it there. What happens if it's dealing with some kind of an emergency? 20 seconds is a very long time. So you need, if we have a mission to Mars, we need a lot of autonomy. That's why you hear a lot, especially people who talk about deep space mission. They says the only way to do this is a lot of autonomy. Some situation we can control from Earth, but a lot of situations they have to deal autonomously, and they have to deal with all kind of contingencies. The beauty here is that these are what we call reactive plans. Remember, there is input, so the environment is not totally under your control. You observe the environment, and then you do something. This is in fact, there is I think in the military term is it's called the OODA cycle.
It's an observe, orient, decide, act. Is that it?
Yes, exactly.
Okay.
Observe, orient, decide, act. So basically observe, see what's going on. They call it military term is situational awareness, understand what's going on, and then decide what you need to do, and then you do it. And again, one of the issue is that, you send Team SEAL, what is it? SEAL Team 6. You send them to Pakistan after Bin Laden. They don't have, they can put on the radio, well, we have encountered now.
Here we are.
We encounter
We're undercover.
We have a locked door. What do we do? Okay. You guys, you're on the ground. Okay. You can't wait for Obama to tell you what to do. You have to act autonomously. Okay.
That's right.
So if we're going to have really kind of agentic AI, then we want autonomous action, taking all kind of contingencies into account and deciding and acting. Okay. And temporal synthesis is exactly the engines to do that. Now, temporal synthesis as it stands today is purely symbolic logic. Okay? There is questions now, so right now we have two kind of big questions to me. One is, can we get scalability or tractability so we can deal with real life problems? The beauty of what happened in model checking was it went from really very, very academic to dealing with real life problem. Engineers in the industry are writing specification in SVA, and the engine is going to verify that the circuit satisfies this. This happens today as we speak. We've made enough progress for this to be industrially applicable. This is one. So this is one. Can we do the same thing for temporal synthesis? Okay. The second question is, what about all this progress in machine learning and deep learning and LLM? Can we leverage that? And that is one of the hottest questions today. And there are now events for what's called neurosymbolic reasoning. Can we combine? We have these two successes. The one that got more public attention, which is neural nets, deep neural nets, and one that also had amazing success but less public attention, which is symbolic reasoning. Can we combine the two types of reasoning? Now, why do we think that we should be able to do it? Because that's what our brain does. So Daniel Kahneman wrote a book about 15 years ago, and he described system 1 and system 2. Okay? So what is system 1? You go from your tribal village, you take a walk in the savannah, and you see something yellow moving in the tall grass.
Red alert, right?
You say, this is most likely a lion. Get the hell out of here. Okay.
Yeah.
And you do not say, I'm going to go and collect some fishes and subject them to DNA analysis. You make it is called fast thinking. He talks about fast and slow thinking. Okay.
Yeah.
This is system 1. This is fast thinking. Skadoodle. Get the hell out of there. Fast. Okay. And we don't, when you meet Mark, you don't say, okay, let's look at facial feature, the shape of the lips. Let's see. It's Mark, okay? You don't have to think. There's no logic. It's just pure. It's a system 1. Fast, you immediately know. It doesn't take you. Immediately, this is Mark. Mark, look at you and know this is Brian, okay? We don't have to think about it. However, go back to this person that went back to the village and warning all his fellow villagers, there is a lion near us. Let's go hunt the lion. They're going to make a plan. You go here, you ambush there, you make noise, you scare it. We will, do that. This is not what's called system 2. And we do that. We have both system, and we don't usually stop to say, was that system 1, that system 2. We kind of interleave them, and they operate together very, very smoothly. So smoothly, It's actually quite amazing, because they're very, very different systems, okay? One sits here in the back of this, what we call the lizard brain, and we have the frontal lobe, which are very well developed. And that's where we do symbolic reasoning. That's where we have what we call slow thinking, and we integrate them. And so the goal, the holy grail I argue, and many people argue today, is to leverage on the success we had in symbolic reasoning, the success we had in neural reasoning, and to combine the two. This is I would call it, with temporal synthesis, it's fairly mature, okay? We are not quite there that I can claim industrial success, but I kind of see us getting there, okay? We are very close, I think, to getting industrial attention. Industry will say, because one thing the industry can do is what you cannot do. They can build real software, not hardware, okay? They'll build a tool. The tool will be maintained and improved, and people will work on it, okay? Industrial production, okay?
Moshe, we've got great news for you. There's quite a bit of industrial efforts right now. This is NDIA's main focus, is combining these System 1 and System 2.
Fantastic.
It's happening, Moshe.
This is to me now, this combining System 1 and System 2, that is now to me in AI, that's kind of to me the holy grail of AI today. Okay, the holy grail now. How do we? Because it's what we do. You look at this is what Kahneman told us. The human intelligence combine, not always, but very often seamlessly, these two very different type of intelligences. Okay, and that's part of what human intelligence is. So if we want to try to create machine intelligence that would kind of mimic human intelligence, we have to be able to do both and integrate them, not separately, but integrate them. So.
Ask a side question, Moshe. While this whole scaling we were talking about before, everyone's obsessed with, scale is all you need in this transformer world. Were you having this thought that no, it's going to take a combination of the two things if that's the existence proof of the human brain?
I'm thinking for a while. Okay, I have let's suppose I have a lawnmower, and it could be a fantastic lawnmower, even an autonomous lawnmower. Okay. But I will not go to the lawnmower and says, okay, this is a great lawnmower. How about doing the laundry also? I said, no, it's a different tool. Now, it's a different tools. So LLMs have been really done an amazing job. I mean, there was all the issues that we still have there, hallucination, and, some people call it hallucination is all you need. We still, but it's an amazing progress. I just asked ChatGPT to write, I told it, write a 500-word story about Moshe Vardi, the astronaut.
Well, I like that.
It wrote a lovely story, I have to say. It wrote a lovely story. And it combined what it could find about Moshe Vardi and logic. And it talk about logic and using it to solve mechanical problem in space, save the mission using logic. It was a lovely little story, okay?
I liked it.
It's an amazing accomplishment, okay? So we have this great success. I said we have automated reasoning that when I was a graduate student, it was a pipe dream. Nobody said it's NP-hard, forget it. This is not possible. And today the fact is industrial reality, huge progress. And now it's not about how do LLM do reasoning. To me, how do we integrate? LLM are great in what they're doing. How do we integrate LLMs with symbolic reasoners? And how do we integrate that they operate seamlessly, okay, rather than clunkily? And to me, there is a little bit of this integration, chain of thoughts and this, but I said, take the success that we have with symbolic reasoners, leverage on it. It's not saying, no, we want to do it all inside the LLM world. To me, it doesn't make sense. You have a tool. It's right there. It's on the table. And you say, no. I need to take a screw out. Yes, I have a screwdriver, but I want to use my pliers because I'm a pliers person. Okay.
Right.
You have a screwdriver.
Let's see how big the pliers can get. How many,
Use the damn
Let's just tack tools on top of the pliers, right?
Use the damn screwdriver. It's right here. Doesn't cost you money. Okay. Just use it. So I have to say, this obsession with, and there are lots of argument why scaling is not, we have kind of, people are debating it. I'm not an expert on this, but there is kind of a debate whether would scaling take us to AGI. And I said, if we really want to capture human intelligence, we have to capture system 1 and system 2. And that will require both neural reasoning and symbolic reasoning. Now, it's true, you can argue we don't need symbolic reasoning because the brain at the end are just neurons, okay? There are no, if you open my brain, you will not find for all X, there exists X inside my brain, okay? But in some sense, you can say logical reasoning in the brain is software runs in the brain. And it's a huge part of human intelligence. So, for example, take something very simple, numbers. Where do numbers come from? There are no numbers in nature. You have 2 lions and 2 monkeys. We had to look at them, say they have something in common. The 2-ness is something that is common to 2 monkeys and 2 lions. And so we came up with the concept of 2 as an abstract concept. In my brain, you will not find 2. But imagine now I tell you, okay, guys, you have no numbers. You cannot use numbers. Do AI without numbers, okay? And not only that, we looked at 2 numbers, 2 lions and 2 monkeys, and we look at 3 zebras and 4 rhinos, and 3 zebras and 3 rhinos, and we said, there's something common to the 2 and the 3, and we came up with the concept of numbers. So abstraction is a huge part of human intelligence because we couldn't have language without abstraction. Okay? For example, James Bond walks into a bar. What does he say? He doesn't say, I am James Bond. He says, my name is Bond, James Bond. James Bond is a symbolic name for, who am I? I am who I am. God answered it when when Moses asked God, who are you? God says, I am who I am. Okay? Now we can give me names, but the name is not my identity. Okay? James Bond, understand it. He says, my name is Bond, James Bond. It's not who I am. How to define who I am? My name is Bond. But the idea of abstraction, of symbolic reasoning is we don't have intelligence without language. And language is very much about abstractions. And so I'm convinced that the way we will reach forward is to combine different type of reasoning that we have. And right now we have neural. I mean, there is something in between with what I'm working. So classical logical reasoning is about just true and false. But as soon as you start going to neural nets, you realize that you need also quantitative reasoning. So partly where I get into this is by looking at quantitative logical reasoning. That is to say, if you have a logic sentence, not is it true or false, but can we give degree of truthiness? Mm-hmm. Degree of truthiness. For example, suppose that I'm making a very simple assertion, P and Q. And now you choose P and Q, each one at random. You flip 0 each one, you toss a coin. So P can be true or false. Probability half false, probability half true. Q can be true and false, each one probability half. So what is the probability that P and Q will be true? 1/4. But if it's P or Q, then only one of them has to be true. The probability is 3/4 that P or Q will be true. So this is what I call degree of truth. So now we're taking what before was just absolute truth into degree of truth, which is quantitative. And so there is a project that not just me, but there is people who are trying to take logical reasoning and make it quantitative. And we believe that this is an important step towards the integration of neural and symbolic reasoning. Partly because if you look at the basis of neural reasoning, it's quantitative. Because you have, the neuron fires, and then you have like ReLU gate or tonnage gate. You have actually numerical computation inside the neurons, okay? So we're saying, okay, so logic was purely about true and false, but we need to quantify it, and that will be a step on the way towards this holy grail integration between neural and symbolic reasoning.
Very cool.
Cool initiative.
I before we go too deep into the probabilistic stuff, I just want to come back to the temporal space for a moment.
Mark's favorite thing. He is obsessed with temporal logic.
Yeah, just to mention that there's ArcAGI, or in combination with NVIDIA, has launched or is going to launch ArcAGI 3, which is this interactive reasoning benchmark where you actually try to solve games that unfold over time. And it seems like there's a lot of overlap there, so it might be an interesting direction to look at.
Yeah. Actually, I have a student who looking into Arc 2 right now, into one of the Arc 2 benchmark problems. But this will be in the Arc 3?
Yeah, Arc 3 hasn't been fully officially released yet, but there's some preview tasks out there, and those are have a temporal nature to them.
Okay, I'll take a look. Thank you for the pointer. I didn't know about it. So
we'll send it to you. I'll follow up on that.
Yeah. That's the story. We're kind of closing to an hour and a half, and I give you kind of a big story here, going back big story, going in the foundation of mathematics, okay? But I don't know if you read Yuval Noah Harari, like Sapiens, very famous book, Sapiens. So he likes to do like what some people call big history, okay? Or like Jared Diamond, kind of Gun, Germs and Steel. These are kind of big history. So I kind of sometimes like to look at mathematics and computer science and do this kind of big history to see how ideas unfolds over sometimes hundreds and thousands of years.
I love it. And then also just that these ideas that are kind of becoming more popular or we're digging back in again came from before. And you do a great job of giving people behind these ideas, like who the origin of these ideas were, is very helpful.
There's always the human story. I mean, here I didn't get into, but they're always kind of, these are, I try to do it when I teach logic. I try to get into the personal stories. And partly because it's important for the students to, first of all, to know that, when you open a textbook, you think, okay, science arrived as a cake. It's just all made up. Or, okay, here it is. Somebody thought of the whole edifice. No, it goes step by step, and there is a mess in the middle. And over time, we polish and we cut this piece off and that piece off, and it comes out polished. It doesn't immediately jump nice and clean. It's done by human beings. They're flesh and blood human beings. They have life. Sometimes their life is good. Sometimes their life is tragic.
You're amazing, Moshe. This is just like your breadth of knowledge is incredible. And like, your personal experience to kind of back it up is just, unparalleled. I guess, do you have any parting words for folks who are maybe, let's say, the majority of folks will probably be, know about LLMs, but they're just getting exposed to this, symbolic side of things. Do you have any advice for people kind of, leveraging this?
So I'll give what we call shameless plug to another talk that I recently gave, and which was labeled, "What is Theoretical Computer Science?" And I argue, because some people have defined Wikipedia, for example, defined theoretical computer science as a branch of mathematics. And I argue it's a bad metaphor. Because mathematics, we kind of have given a permission to mathematicians to do things just for the aesthetics of it, okay? I mean, we can debate why is society paying mathematicians to do things just for the aesthetics, okay? We're paying mathematicians better than we're paying artists or musicians, okay? So what is it about it? But in particular, I argue that theoretical computer science should think of itself more like theoretical physics. Theoretical physics is very mathematical. You can go into see very, very advanced mathematics in theoretical physics. However, even theoreticians, if it's not theoretical physicists, they're real physicists, they're not theoretical physicists. And they understand their theories have to explain and predict the world. If you have a mathematical theory, physical theory, that at the end does not do a good job at predicting, explaining the world, ultimately it will be dismissed. I'm hearing now that I remember that where string theory was a very, very hot thing, and today more and more people are questioning it to say, is that a physical theory? Does it explain and predict the world? I'm not an expert on it, but ultimately the test of a theory has to explain and predict the world. I claim that the same should be true for theories in computer science. At the end of the day, they have to explain and predict the world. And so what happened here, for example, that there are people thought it's NP hard, so we are done, there's nothing more to do. And other people says, we're going to build tools. We're going to see what we can do. And we have huge success because of the people who said, forget about the theory. Let's see what we can do in real life, real tools, real problems. We know that it's hard, but there is something special about human-generated problems. They seem to be not that hard. Let's focus on that. And so I think the idea is we need theories because theory gives you kind of abstraction. You throw away kind of, you're not drowning in the detail. You create more abstract way, and it's easier to kind of think of solution in a more abstract way. But then you have to fold up your sleeves and see, okay, let's reduce it to practice. Let's see whether it explain, predict the world. And I think this attitude, that's what I expect my students to do. That's advice I would give to people. By all means, develop theories. But don't forget, the theories have to explain and predict the real world. So that's my parting thought.
Thank you, Moshe. That's amazing. And you've really lived that advice too. So you are
I started as so to speak, pointy head theoretician. But
it came around to practicality.
But at some point I said, wait a minute, let's see how does that work.
Moshe, I have to tell you, I actually assigned that reading just a couple weeks ago as the start of the semester here at Columbia, and I have a class of 300 students. I had all of them read that article.
Fantastic. Hopefully they will be influenced a little bit, some of them. Okay,
certainly.
Very good. Cool. Very nice.
Moshe, thank you so much for your time. We really appreciate it. Thanks for coming on.